particle experiment, about 1 in 10,000 alpha particles are deflected by more than 90 degrees. Assuming this probability is equal to the ratio of the cross-sectional area of the nucleus to that of the atom, estimate the diameter of the nucleus for atoms of diameter 0.5 nanometers in a metal foil of thickness 10 micrometers. Alright, so let's just jot down and make sure we understand what they've told us. So they've got the probability of being deflected is on a given layer is the area of the nucleus divided by the area of the atom, and those are cross-sectional areas. They've told us the diameter of an atom is 0.5 times 10 to the minus 9 meters. And they've told us they've got a material, and that obviously is made up of these atoms in rows or columns like this. And the thickness of that is 10 times 10 to the minus 6 meters. And they want us to find the diameter to estimate the diameter of the nucleus. Now, okay, let's just look at this. So the diameter of the nucleus is going to be in here. PL we've talked about in part 4a, so we've got an equation for that, and the area of the atom we can work out from dA because it's just going to be pi r squared. So if we actually look at then, if we rearrange this, we can say the area of the nucleus is equal to the probability of being deflected off one layer times by the area of the atom. Now that means from the previous question we know 1 upon 10,000 n times by A, because the probability of being deflected off of one layer of atoms is 1 upon 10,000 n. So if I look at that then, well, I can simplify this a little bit more, because what I can do is go, my area of my nucleus is going to be pi, diameter of the nucleus upon 2 squared, because it's pi r squared, is then going to be 1 upon 10,000 n, pi, diameter of the atom divided by 2 squared for pi r squared. And I can simplify that equation down, which obviously the pi's cancel and the divide by 2's cancel. So I get the diameter of the nucleus squared is 1 upon 10,000 n, the diameter of the atom squared. Now I know the diameter of the atom, I was given that. The only thing I don't know then is n. Now n is the number of these rows of atoms I've actually got making up this piece of metal. So I know the number of atoms then is going to be the thickness of the metal divided by the diameter of one of the atoms. The thickness they gave me was 10 times 10 to the minus 6 meters. And they've told us the diameter is 0.5 times 10 to the minus 9 meters. Now what that's going to give me then is, well, that'll be 20, 3 times 10 to the 3 actual rows, or 20,000 rows. Alright, so let's have a look at what that means. Well, I can substitute in for n, and I can also actually then simplify and get down to a final answer by taking the square root of this side. So I can say then that dn squared is 1 upon 10,000 times by 20,000 times by dA squared, and actually the square root of it. I can actually simplify even slightly more, so I can go 1 divided by 10,000 times by 20,000 square root times by dA. At this point, if I substitute those numbers into my calculator, I've got 10,000 multiplied by 20,000, 1 divided by that answer, square root of that, times by dA, which is 0.5 e to the minus 9, gives me an answer of 3.5 355 times 10 to the minus 14 meters for the diameter of this nucleus. Now, if I go back through, everything I've been given is actually really only to one significant figure. So I would quote my answer when I go 4 times 10 to the minus 14 meters to one significant figure. Now, I do note the book itself gives an answer of 3 times 10 to the minus 14 meters. Now, my argument for that is, well, to be honest, there is going to be slightly different rounding, I suspect, is going to cause that problem because we're so close and we only have to be 0.04 times 10 to the minus 14 less, and I would be rounding down. So I think that's the correct answer. Thank you very much.